In this video, we'll introduce a topic that's pretty unique to microcontrollers, that of interrupts. The idea behind an interrupt is that our code runs sequentially. So we're in our infinite loop inside of main, and maybe we're doing things like we're reading buttons, and we have 3 buttons. So to see if the button has been pushed, we check to see if the level of the button, so we read the port and is it currently high, and the last time we read it was low. So if there's been a change, we can decide, yes, that button has been pushed. So if the button has been pushed, we'll then run some code like, do some math or print or scans, things like that. So we have 3 buttons, so we have to check one button, and then we check the next button, and then we check the next button. And as fast as we can, we loop, and then we check all the buttons to make sure we don't miss an event. Because if our code runs too slowly, and someone goes and pushes a button and releases the button at an instance that the code didn't check to see if the button was pushed, we would miss that event. That is pretty hard to do when the PIC runs at 80 megahertz and our code is pretty simple, but you can imagine having, say, I don't know, a keyboard's worth of buttons and lots of code to run if a button is pushed. So the code starts to slow down and you could miss events. That type of system is called polling, where just polling to check, is this pushed, is this pushed, is this pushed? That's different than the concept of an interrupt, where we can initialize a pin to pause whatever the CPU is doing at the moment an event occurs. So that event is called an interrupt, and we can use a variety of interrupts with all the peripherals so that if an event happens, we can pause what the code is doing, go deal with some short amount of code because the interrupt has occurred, and then when the interrupt is done, we go back to wherever we were before. So we'll have some nomenclature here. An IRQ. This is the interrupt request. So this is the thing that's requesting that an interrupt occur and pause whatever the CPU is doing at that moment. On our PIC32, there are 96 different events that we could set up to generate interrupts. So essentially, when you look at the big list of all the peripherals that the PIC has, each peripheral, like the pin I/O and the serial communication and analog inputs, all of those have the ability to generate some kind of IRQ. What happens when a request occurs? The PIC will run the ISR. This is the interrupt service routine. This is the actual function. So when the button is pushed, the PIC will pause what it's doing. It'll go to a specific function that we're going to write, and we will declare in a special way that makes it an ISR, so that the PIC knows whenever this event occurs, I can instantly go to this place in memory, run the code that's there, and then I'll go back to wherever I was when I was done. Strangely enough, there's only 64 of these functions. That means that some IRQs will not go to unique functions. Some will go to like 3 different events could generate the same interrupt. So when you get into that kind of interrupt, you might have to check to see, why did I get into this interrupt? Was it one of the 3 things that could get me here? They're usually related though. So the 3 that are tied together might be part of the communication routine for the UART. And so the UART might generate an interrupt because it sent data, it received data, or there was an error with data. So whenever you get into an ISR related to the UART, you might have to first check to see what are those 3 potential cases. Not a big deal. It does slow things down just a little bit, but not by much. You might have a question, well, if there's 96 different events that could generate an interrupt and we turned all of them on, what happens if 2 of them happen at the same time, or one has happened and then another one happens? Do interrupts interrupt each other? Do they queue? Does it like throw them away? So that is the issue of priority. And every interrupt, when we declare it and when we make the function, we will give it a priority level. And the highest level is 7, down to, let's say, level 1, which is the low. I think there's also a level 0, but we don't use it. And there's a sub-priority as well. There are 4 levels of that, so 4 to 1. So how does priority work? Well, when the PIC is running, just in general, let's say it's in priority level 1. So you're in your infinite while loop in main. So if we set up a priority of level 4, like a button push, that means that 4 is bigger than 1. So at the moment that event occurs, somebody pushes a button, the PIC will say, well, I'm currently at level 1, but this level 4 thing has happened. So I'm going to pause where I am, I'll remember where I am at the level 1, and I'll go deal with the level 4. While the level 4 is occurring, let's say a level 7 happens, another button push that we think is even more important. It will pause where it is at the 4, go do the 7. When it's done with the 7, it will go back to the 4, and when it's done with the 4, it will go back to level 1, which is like main. Let's say we have 2 level 4s that could occur at the same time, and one is a subpriority 2 and one's a subpriority 3. So if we are in the 4.2, while we're doing the code in the 4.2, a 4.3 occurs. The 4.3 will not interrupt the 4. So something of the same level can't interrupt itself. But if we have a 4.1, a 4.2, and a 4.3, and we're in a 4.1, and a 4.3 occurs, and before 4.1 is done so we can do the 4.3, a 4.2 occurs, they will queue in such a way that the sub-priorities take precedent. So if you're in a 4.1 and a 4.2 occurs, and then a 4.3 occurs, when the 4.1 is done, it will do the 4.3 before it does the 4.2, even though the 4.2 happened first in time, because the sub-priority sets the queue. Then we also have the queuing of, let's say you're in a 4.1 and a 4.3 happens, and then a 3 happens, it'll go do the 4.3 before it does a level 3, before it goes back to level 1. So hopefully that makes sense. Then there's the concept of context save and restore. The word context means, what are we doing at the moment this interrupt occurs? So the CPU has its own core registers. There aren't many of them, but it's got its own little bits of local memory. You could think of it as like the cache. All the variables that we're currently working on are currently in the cache. When an interrupt occurs, we go to a new function, we start running the code that's there, and we might overwrite the cache or whatever variables the CPU is working on at that moment. So we need to make sure that when our function in the ISR is done and we go back to main, main still has all the stuff it was working on that it hadn't finished yet. So that's the context, the stuff that we have that we need to save. So when the interrupt IRQ occurs, before we jump to the ISR, we're going to take the variables that we have in the context and we're going to put them into RAM. So we're going to save them. Then we're going to go do our ISR. The stuff that was in the context gets overwritten because we are doing functions. Then all gets thrown away when the ISR is done. So when we jump back to main, the first thing we do before we start running code again is we go back to RAM, we copy the stuff that we used to be working on back into the CPU registers. So that's the concept of context save and restore. That takes a little bit of time, right? Because say there's, 32 variables that we're working on. So we have to save 32 variables, go do our stuff, and then restore 32 variables. That means there's a little bit of latency and delay, and depending on, maybe we're only working on 16 instead of 32, so we only have to do 16. So every little bit of time when an interrupt occurs to when we actually do the function, realize that it's happened, might be a little bit different. So we'll see hopefully some ways to optimize out the save and restore. The optimization level hopefully minimizes that amount of delay due to the context save and restore. And we have another thing called the shadow register set. Or SRS. The SRS is a parallel context. So the CPU has all these registers that it works on. In parallel is a whole nother duplicate version of those things that it normally does never use, except for a very specific interrupt. And on the NU32, we've set up priority level 6 to use the shadow register set. So that means when an ISR at priority level 6 occurs, context save and restore doesn't need to happen. Instead, the CPU switches over to this other set of variables, other set of memory inside of the CPU, just starts using those, and it doesn't have to delete it when it's done. It could just go back to the original context without doing the context save and restore. The PIC only includes, or at least this version of the PIC only includes one shadow register set. and we tied it to level 6, so that you could still have level 7, which is super high priority, and then level 6, which is pretty high priority but happens a little faster, and then all the other priorities, which don't necessarily have to run as fast. So when you're thinking about, well, I've got this really important thing that needs to happen, and I need it to happen fast, you would put it at level 6. And then there's still one level, level 7, where you could say, even this one is so much more important than that level. Maybe it's like an emergency stop button or something. You would put that on your level 7. Okay, what else do we have? Before we start looking at some code for how to write things that use interrupts, let's talk about the special function registers. The SFRs, that you have to change to be able to set up an interrupt. This is kind of our first real peripheral other than the I/O pins that we're using on the PIC. So we need to think about what are the SFRs that are manipulated to enable the use of the interrupts. And so the important ones are IFS, IEC, and IEC. So IFS, that stands for the flag. So how does the CPU know that an interrupt has occurred? Well, there's a specific bit called a flag inside of IFS. So IFS is a 32-bit register. So all 32 bits in there represent different flags that could occur. And by flags, I mean IRQs, the things that could say, hey, I have an interrupt, stop doing what you're doing and go deal with me. So this is a flag that will get automatically risen to 1 when an interrupt occurs. So inside of our function that says, okay, here's what happens when this interrupt occurs, we need to make sure to clear the IFS bit for that interrupt, because an interrupt is only created when the IFS goes from 0 to 1. So inside of our function, we'll always remember to set the IFS bit back to 0 so that it can happen again. IEC, the E stands for enable. So this is should the PIC even listen to those flags. So we will set up all the things like how a pin works, and the very last step will be set the enable bit to 1. That tells the PIC, hey, if the flag bit ever goes to 1, go jump to the ISR. Most of the, all of the E bits are 0 to begin with, so that the PIC doesn't listen to any interrupts. So whenever we turn the E bit on, at that moment, that's when the PIC could start generating the interrupts. And finally, the IPC, the P stands for priority. Those are the bits that say, are we priority level 7 with sub priority 3, whatever. So there are 7 steps to using the interrupts inside of your code, or at least we've broken down the process of writing the interrupt into 7 steps. We'll go look at some code in a second to see what are those 7 steps. But they're going to be, set up the peripheral that's going to be generating the ISR, so the peripherals have their own SFRs to write. Then write all the SFRs for the interrupt itself. Then we have to write the ISR, the actual function, and we have to write it in a special way. And then we go back and just double check all of our bits. One more topic is sharing variables. Now, the ISR, the function that we're going to write when these interrupt events occur, they're not a traditional function in that we never call that function. The function gets called automatically when the flag bit goes from 0 to 1, which means we can't pass variables into this function. So if we have a counter, every time we push a button, we want to add 1 to this counter, and we're going to do that inside of an interrupt. Well, inside of that ISR, the function, we need to say, that counter, I equals I plus 1. But how does it know what I is? I would have to be a global variable so that in main it could see what I was, and in the ISR it could see what I was. Traditionally what we do is we probably pass I to the function, and then the function could add 1 and then it would return it. In this case, the ISRs don't receive anything and they don't return anything. So they have to work on global variables. The problem with global variables is that so the PIC, when it's doing math, right, it might go and it might grab a variable from RAM, put it into the context or its special registers, and then rather than saving it back to RAM every once in a while, if it says, oh, it looks like I'm going to use this for a while, it'll just work on it in the CPU register and then eventually return it to RAM, which means that you've got like 2 copies of it. You've got one in the CPU that's currently being used and a place for it in RAM. So here's the worst case scenario. The CPU is working on that variable. It's working on its copy in the context. It's not working on its version in RAM. The ISR occurs. The ISR, when it says go load the variable, it doesn't know that it's in the context. It goes and it grabs it from RAM. It's got the wrong value. So it operates on the value, it saves it back into RAM. When the context is restored, when the ISR is done, now the PIC has two versions and they're both different, and it's using the old version and it overwrites the new version. So somehow we need to tell the PIC during the compilation process, hey, this variable could be used at two different times by kind of two different processes. We're not doing parallel processes here. We don't have two CPUs, but the interrupt kind of works like two processes. They're not happening in parallel, but they can happen, sequentially at the same time. So that means we need to say this variable is a global variable, and it could be manipulated by two different threads. So every time you use this variable, don't save it into the CPU register. Let's always grab it from RAM. It might slow us down just a little bit, but that'll guarantee that we always have the most recent version. So a global variable that's shared, we will define as a volatile variable. So when you say volatile int I or something, and that's a global variable, the volatile keyword in front of int says every time you use this variable, always grab it from RAM. When you're done with it, put it back into RAM, because we don't know, some interrupt or some function might try to grab a bad version. So always load it, and that will prevent the problem of having two copies that overwrite each other. So first, let's take a look at the datasheet to see what all of these bits are inside of the special function registers. So of course the datasheet has 256 pages. That's a lot. We don't want to start just reading from the top. There is chapter 7, the interrupt controller, where you could read a lot more information about how we're using multi-vector mode. There's also single vector mode, which could make things run faster, and you could just read about a lot more details here. But let's just start by looking at, here are the interrupt sources on the left in this table. And these are the different things, the 96 events that could generate an interrupt. We're not going to go through all of them, but they have an IRQ. This is the event number, and that is also called the vector. Another question you might have is how does, if you have two events that happen at the same time, and they're queued up, but they have the exact same priority and sub-priority, how does it know which one to do first? Does it do it sequentially or not? No, it doesn't do it sequentially. It does it by vector number. So this is also a number that could be used to say, well, timer 1 happened and an input capture happened. Which one should go first? Well, this one with the lowest number happens. What we need to know when we start setting this up are what are the IFS bits, what are the IEC bits, and what are the IPC bits, both priority and sub-priority, to know to set up in our code so that we can enable this interrupt. So the core timer interrupt, so we can have the core timer start at 0 and count up to, 40 million, which would be 1 second, and then generate an interrupt. And then reliably, every second we'd have one interrupt to do something like blink a light, and then we could have exactly a 1 second blink. So we would have to make sure that we set the IEC 0 bit 0 to enable that interrupt, and we could set IPC 0 bits 4 through 2 for the priority and IPC bits 1 through 0 for the sub-priority. And inside of the ISR, we would have to make sure to clear IFS 0 bit 0. Now there are so many of these IRQs and ISRs that there are a lot of bits. Look at all these IFS 1 and IFS 2, IEC 0, 1, and 2, IPC 0 through 12. So there are just a lot of these things to find. And if you get them wrong, then of course you're turning on the wrong interrupt. In the 7-step process that we're about to see, this is the table you will look at to figure out what bits that need to be set to do what. Okay, let's look at our sample code. So this is the sample code included in chapter 6. And let's start with the core timer. So we'll look at two different pieces of sample code. So I just explained how we could use the core timer to generate an interrupt that happens exactly 1 second. In, I think, a previous assignment, we've already seen, well, we could use the core timer. We could set the core timer to 0, and then we can do an infinite while loop while reading the core timer is less than some value, don't do anything. That's how we could get one kind of delay. That's called a blocking delay, though, because while we're in that while loop, we're not doing anything. So instead, what we could do is we could have the timer-based interrupt occur, and while we're waiting for that event to happen, we're waiting for that 1 second to pass, the code is running other stuff inside of main. So, what are we doing? We include nu32.h as usual. Now, if you go in there, that includes two things. It includes xc.h, which eventually includes our h file for the PIC, which gets us the names of all the SFRs. It also includes another h file, and that's the one that gets us the definition for this specific function right here. So anytime you see this underscore ISR function, this is how we write an ISR. The ability to do that came from including nu32.h, which included something else. So we'll come back to this. This is we'll kind of like look at main, and we'll come back to the ISR. So here's main. We call nu32 startup. We always do that in every nu32 code. And now we want to turn on the interrupt. So the dangerous thing about the interrupt is that you don't want to be manipulating the bits of the interrupt while interrupts could possibly occur, because you might, change something about how the interrupt works. The interrupt occurs in the step between, before you're done manipulating how the interrupt occurs, and then the PIC gets lost. So there's a __ built-in disable interrupts that tells the CPU, ignore all interrupts right now, because I'm going to start manipulating these interrupts. Then we're going to set for this specific peripheral the CP0, so that's our core timer. We're going to say, when you get to this value, generate an interrupt. And we defined core ticks as 40 million, so that's exactly 1 second. So when the PIC first turns on, that core timer is at 0, and every other clock cycle adds by 1. So it's just sitting there in the background, counting. Whenever that number hits 40 million, it's going to generate an interrupt. So now we don't have to sit there in an infinite while loop or an if statement and constantly see, read the core timer, does it equal 40 million? Read the core timer, does it equal 40 million? That all happens in the background. So this is kind of like we've got a separate thread running, but this thread only runs one specific command. It just says, is the core timer equal to 40 million? Okay, we're going to set the interrupt priority to level 6. So that's using our shadow register set. We're going to set the sub priority level to 0. We're going to set the flag to 0. So just in case that flag was high already for some reason, let's just clear it to make sure as soon as we're done with this code, it doesn't happen. We will enable the interrupt. So now the PIC is going to start listening to this specific flag to see, should we generate the interrupt? We'll turn on the ability to listen to any interrupt at all. Then we will set the core timer to 0 so that we kind of start fresh. At this point, now the core timer is sitting there, it's counting. Our infinite while loop is empty because we don't need to do anything else in this code. So we're just going to sit here and do nothing forever. And in the background, the CPU is looking at the value of CP0. When it hits 40 billion, it generates an interrupt. So the flag gets risen to 1. Context save and restore occurs. In this case, there's nothing to do because we weren't working on anything. The infinite while loop was empty. It knows to go to the core timer vector. So it knows to go to the core timer is vector 0. So it knows to go to this location in memory to run this function. It knows that we're using the shadow register set at level 6. An important thing is that this level 6 needs to match this 6, or you get a bug and it doesn't really work. We have a name for this function, core timer ISR. You can put whatever you want here. We never call this function. This function is automatically called by the interrupt. So you call this whatever you want. We just give it a name so we remember what this function is. And it's a type, it receives a void and it returns a void because ISRs can't receive or send anything. So if we did need to manipulate a variable, we would have declared it up here. So it would be a global variable and with the keyword volatile in it. But in this case, we don't do anything. So we're inside the ISR because 40 million ticks have passed. We need to clear the interrupt flag. So ifs0 bits.ctif. That's the core timer interrupt flag, so that must be bit 0 inside of ifs0. Let's make it a 0, because if we forget to do this, the next time the core timer hits 40 million, that flag will be made 1, but it was already 1, and it's the changing from 0 to 1 that generates the interrupt. So remember, inside of the ISR, you definitely have to set its bit, the flag bit, back to 0. Okay, then that's all you have to do. Now we do whatever we wanted to do when this function was generated. So in here, we're going to invert 2 bits. These are our LED bits. In fact, actually, this is just 1 bit. So we're just blinking 1 LED. Then we're going to set our core timer back to 0 and remind it that it will generate the interrupt at 40 million. Once it's done with this, it goes back to main. It doesn't do anything main. It just waits until it's 40 million. The interrupt occurs. We clear the flag. We flip the LED bit, and we say, now I'll do it again. Okay, so that was a relatively simple version of an interrupt. Here's another one, the external interrupt. So as I said, all of the SFRs can generate an interrupt in some way. One of the hardware versions of this is when a pin changes from low to high or high to low or changes at all. Those are called external interrupts, and only some pins can do external interrupts. We'll go take a look at what pins can do that in a second. It would have been great if any pin could do that. That functionality is called change notification, and there are lots of pins on the PIC that could do change notification, but still not all of them. But when change notification occurs, one interrupt is created. So like 30 pins can generate a change notification interrupt. The first thing you have to do inside a change notification interrupt is figure out which pin generated the interrupt. So an external interrupt, like this example, is more specific because it's saying external interrupt to 0 is one specific pin. And we only get, I think it's like 5 of them or something. So not many pins can generate an external interrupt. It's kind of very special. So we'll start main. Startup, disable all the interrupts. Here's the bit that says, hey, PIC, listen to the int0 pin and the int0 EP. When that's a 0, that means we're going to listen to the int0 pin when it changes from a high to a low. That's a falling edge. Generate an interrupt. So depending on what kind of special, what kind of peripheral you're using, sometimes there's many lines here. So like on the previous example, we used a function to tell the PIC to use the core timer, and we set the value that it should listen to. That probably took several special function registers to listen to. So in this case, this is pretty simple. There's only 1 bit to set to turn on, to say how this interrupt is generated. Okay, we're going to have priority level 2, subpriority level 1, clear the flag, enable, global enable. Again, in the infinite while loop, we'll do nothing. When the interrupt is called, we have to make sure this IP2 matches this IP2. Because we're not 6, instead of SRS, we're soft. So soft means that this is a software interrupt, so we have to do context save and restore. Give our function a name, which doesn't really matter. Okay, in this case, what are we doing? We're saying turn the LEDs on, set the core timer to 0, wait a certain amount of time, turn the LEDs off, clear the flag. So this, every time you push the button, the LEDs will turn on for a very specific amount of time and then turn back off. Let's go back real quick to the data sheet, figure out what pins are capable of being, I don't know, external interrupts. The external interrupt ability is actually part of the ISR chapter, so that's in here somewhere. Well, because this is the datasheet, not the family reference manual, it's not going to say. But if we take a look back at the picture of the PIC, we know it's the int pins that can be external interrupts. So let's see if we can count how many int pins there are. And our textbook specifically has the picture of the PIC that's a little easier to find. We'll, there we go. Here's our PIC 795F512H. Here is the int0 pin. So pin 46, or how it's referred to on the PIC32, pin D0. So if you put a button on D0 and you made it an input pin, then you could enable int0 and figure out when is that button pushed. And any other pin here that says int, so there's going to be int 1, int 2, and 3, those could also be external interrupt pins. Here's int 4, here's int 3, here's int 2, Here's int 1. They all happen to be next to each other. That's nice. So D8, 9, 10, 11, and D0. Those are external interrupt pins. Note how they're also 5-volt safe, just in case the thing that's generating your interrupt is sending you 5 volts for some reason instead of the normal 3.3. Okay, so this was my overview of interrupts. Give the textbook a read to make sure everything makes sense. The homework assignment is going to have you set up a bunch of SFRs to do this. In my next video, I'm going to talk about specifically, there's many ways to change SFRs. Let's find the best way to do that. And then review those 7 steps. Convince yourself that you can write in a function that occurs when a timer-based or button push interrupt occurs. And your homework assignment is going to be to build a stopwatch where the button generates an interrupt to remember how much time has passed.